Okay, let's start lecture. And welcome back. We didn't have any homework over the weekend, which I know is a disappointment to many of you and kind of, cuts the wind out of your sails a little bit. But we're going to have some get your clickers ready. We got a ton of clicking to do today. Just one of those days I feel like, I've got about 7 or 8 questions. So get those ready, turn them on. Just to remind you, SI will be running Wednesday. Did you have a session yesterday, Monday? Okay, Martin Luther King Day. Yeah, okay, so Wednesday 2 tomorrow, and then another on Thursday. And it's not. Oh, switch me over to laptop. Sorry. Right. So here's the SI schedule. Try to get to that if you can. And even 1 or 2 sessions per week is going to really help you a lot, in my experience. Okay, turn on your clicker. We're on frequency BC, and you'll get the Go Nitro message if you're on frequency BC. If you don't have frequency BC, what you want to do is hold the power button down until it flashes, and then type in BC. And that'll set the frequency. You'll get a check mark, and then the Go Nitro message, and then I think it'll say welcome or something like that. Okay? Raise your hand if you have Go Nitro. Only 2 people? So nobody saw the Go Nitro message? It doesn't? Oh, let me take. Okay, so we're going to do some multiple choice questions. Go ahead and turn your clickers on. You should get the Go Nitro message. Yeah, okay, I got it too. All right, good. Now who's got the Go Nitro message? And a lot more people. Good. It's very brief. It'll say Go Nitro, then it'll go to welcome, or it'll go to ready, I think. Okay, now we're going to do some clicker questions about this velocity graph. So go ahead and make a good sketch of it. From 2 meters per second, from 2 meters per second up here at the start to minus 2 meters per second after 2 seconds. And that's indicated down here in this little list of data. Can you move forward, please? Always in front of row K, never behind it. And so it's Vx. So the x component of the velocity. So this doesn't say anything about how it's heading in the vertical direction, the y direction, but left and right. Okay. So the upper half means rightward motion. The lower half means leftward, because that's where all the negatives are. Okay. And it's going, and I just graphed it out for 2 seconds. All right. So the graph itself is the fuzzy red stretch. So get a good sketch of that. And here's our first question. And you still have the graph, so you can keep jotting that down. Go ahead and take notes on each of these questions as well. Okay, frequency BC. What does the graph show? Type in a letter A, B, C, D, or E. You can walk around if you want.
Yeah, we'll at the end.
Okay.
So I'll talk to you after class if I need to, except I've been here since the first day and my iClicker has been registered, but you read my name as someone who hasn't been registered.
Yeah, what was your name?
Brendan Epstein.
Talk to me after class.
Okay.
We'll try to get it sorted out. Okay, 10 seconds to vote, starting right now. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, And now look at these answers here. There's a whole spread of answers. Okay, and so let's talk about the disagreements here. The graph is above the x-axis for 1 second. The speed is changing, but it's a positive speed, so that means it's moving this way. But it's slowing down. It's getting slower and slower. So somewhere over to the right, it stops. That's where it crosses the time axis. V is equal to 0 there. All right? And then it goes negative for a second. Right? So that means it's going back over this way. All right? For another second. All right? And then that's the end of the graph. So for this one, let me get my cursor back over here. The correct answer is that it initially moves horizontally to the right, over this way. Then it comes to a stop just for an instant. And then, so it might be like something on a spring. It goes all the way out to the furthest extension of the spring. And then it stops just for an instant. And then it starts coming back towards, where it started. All right? Yeah.
So a question about this, I thought that the graph represented something at the rate at which it went and how far it was going in a direction. How do we know by the speed and how fast it's going to
Because on a velocity graph, it's the x component. And as I explained before the question,
right.
Anything in the top half of the graph above the timeline is a positive number for v subscript x, correct?
Okay.
So that means you're moving that way. Now you might be going slow or fast, but at least if it's positive, you're going that way.
And this is going towards the direction of the graph?
It's not the graph. Don't think of a graph like this as a picture.
Okay.
It is not graph paper. It is not. It is an abstract graph. So it's not like looking at something on graph paper.
Okay.
Okay. Where you go. It's not a point A to point B type of a graph, right? This is a velocity graph. It shows the value of the velocity. Okay. So down below the t-axis, it's negative. Now there was a question over here. Yeah. Go ahead.
How are we supposed to assume that it moves horizontally to the right from the fact that it starts at 2 meters?
Yep. Yeah. So it starts, somewhere like right here, 2 meters per second, and then it's moving to the right. It's slow, but it's slowing down. So at a certain point, it's at 1 meter per second, and then it's at half a meter per second, and then it's at 0 meters per second. That's right. That's right here. Right here is where it's 0 meters per second. Stopped, but just for an instant. Because now it starts acquiring negative velocity. So that means it's going left. So your blaze starting to blaze over. Now you start out slow. Okay, so these first few instances of time here, it's going left. Yeah, it's negatory, but it's not that fast. But down here, you're going negative 2 meters per second by the time you're down here, by the time the system has evolved to that point. So now 2 meters per second is about 4 something miles per hour. So that's a walking speed. It's like 4.5 miles an hour. Okay? All right. So the way that you would do it is somebody starts walking at 4.5 miles an hour rightwards, they stop, then they turn around and they walk 4.5 miles an hour back this way. Or they get to 4.5 miles per hour eventually after 2 seconds of accelerating. It's accelerating. Speed is changing. Okay? Continue.
Okay, so is the line just purely velocity?
That's correct. The line is purely velocity. And remember, this is an abstract graph. So, we're learning about science. We're not doing geometry class here with X and Y graph paper, at least not all the time. Okay? And this is an abstract one. You can't take a photograph of a bug on this line because it's not XY graph paper. You could get a piece of XY graph paper and train an ant to walk along a line, and that's nice. You can make a movie of it. This you can't make a movie of it. But it still has physical meaning. And you could translate it into English sentences, as I've just been doing for the past few minutes. Okay, question.
So for this graph, like an example of it that would having a real world, like what would go with this type of graph, like pushing a ball on an upward slope, like it's going up and then it slows down, stops, and then comes back down.
Yeah, that might,
Okay.
yeah, something like that.
All right.
You know, you hit the slope with maximum speed, then you start going up the slope and slow down, and then at some point on the slope, you stop and then start sliding back down
I see.
and return to maximum speed.
So going rightward is another way of kind of saying going forward, and then leftward is kind of going backward in the sense.
Yeah, that's a good way to put it.
Okay, thank you.
Yeah, if you think about left and right or forward and back, you know. All right, let's go to the next question. Actually, this is commentary on the question. So here's the positive part. So up here where this arrow is, that's where you have positive value of v subscript x. So that's where you're walking to the right or moving to the right in some way. And then down here, this is where you have negative. You're moving back to the left. So delta x is going to be from big X to small x. It means you're changing position to the left. Your speed is going to be negatory. All right, and then right here, right here is the point at which you stop somewhere over here to the right. Okay, you stop. V is equal to 0. All right. Now the reason we're going through these questions on this graph is so that you can understand these graphs because they have a lot of meaning and I'm going to use them a lot. All right. Here's another question. You know, you've heard of rise over run. What's the run of this graph? 2 seconds. What does that mean? See, because you're always trying to figure out what this means, and if you can write a good sentence about it, as we're doing here, we're forming a sentence, then you understand it. Okay? And we want to write a true sentence, and we want to avoid writing a false sentence. I had an earth science teacher in high school, and he was famous for his wrong answer tests, where he wrote the test. So there was only one wrong answer for each question. You had to find it. What a guy. But this one is, okay, 5 seconds starting now. 5, 4, 3, 2, 1, 0. Good. I see you guys getting your numbers in. All right, let's see what you guys voted for. Aha! This one is a little bit stronger philosophy for answer C. And let's see, let's just take a look at this. Here's the run, okay, this bracket from 0 to 2 seconds. So that's the width of my graph, you know, and I could have graphed up more, but I just decided, okay, I'll just graph the first 2 seconds. Okay, so my run is the first 2 seconds of the motion. All right, and that's the duration of the motion. So C is actually correct, and I'll just grade that one correct. Okay, and you can see here, I'll show you what I just did. You can click in this software, you can click and unclick answers. See, here's what it looks like if I don't click the correct. Here's what it says. Here's what it looks like when I click incorrect. The correct answer. So it's pretty nice software the way this thing works. Okay, next question. All right, rise over run. Let's talk about rise. Okay. The rise is -4 meters per second, i.e. it's dropping from left to right. Okay. So we say it's a negative rise or it's a dip, whichever way you want to say it. All right, so the meaning of that is what? And you could talk, when we're doing clicker questions, you could talk with your neighbor. I encourage you to do that. If you feel like you want to consult with them about anything, go ahead and do so. Okay, if you're sitting with somebody, and right now, no, oh my goodness, are those grapes?
No, those are blueberries.
Oh, Yasmin is sitting unaccompanied up here with a gigantic bag of blueberries. They're so big they look like grapes. But anyways, if you want, if any day you want to come up here, sit next to Jazz, she can have one on her right, one on her left, and that's a nice way to study. Same with the TA, Anna. She usually my TAs when they're not helping me with various tests, they're sitting in the front row, and then you can sit next to her and get some coaching during class. All right, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh. This one's got a little bit of spread in the answers. Let's take a look. Okay, the meaning of the rise is here. On the graph itself, it's a dip of negative 4 meters per second. So what that means is that's the change in the velocity, delta V. Okay? And it looks like that was most people the biggest group got that one right, but more people answered incorrectly on that, which, that's all right. You want to, missing a question in class where it's a participation grade is all right. On the test, you want to get it right. So, and just as a little advertising public service, now she's eating the blueberries right in front of me. Gosh. The only thing worse would be like Doritos or Chick-fil-A strips or something like that. Good. I'm glad you're not going to do that. But anyways, clicker questions are always a good thing to study for exams. All right? Just to, so you know. All right, next question. Rise over run question. Number 3. The rise over run for this graph is negative 2 meters per second per second. All right, now the meaning of this is what? A couple some years ago, 4 or 5 years ago, I had in the other lecture hall, one of my students would almost every day bring a bag of Doritos or Fritos or something and deliberately eat them right. And she would sit in the front row. But she was a good student, and she came to office hours a lot and stuff, and I eventually asked her to be the SI leader. So she became the SI leader for a semester, for a year. And she was a pretty good SI leader. But I never forgot that trick with the Doritos. It was just about every day. It was really distracting. Okay, 10 seconds to vote, starting now. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Now you've gotten about a minute for each of these questions, and on an exam, that's how I design exams for time. Yeah, so option B is correct on this one. Glad you guys got that. The rule of thumb, one of my old supervisors said, Dr. Brickner, for a Scantron exam, use 1 minute per question. So if we have a 50-minute exam, we have 50 questions on the Scantron. That's how we do it, or that's how I do it. Okay, next question. So, no, this is the same question. Right? It slows down, it stops, and it starts acquiring leftward speed. So the whole time its delta V is negative. It starts with some positive, but it acquires some of this, i.e. it's slowing down. But then when it slows to a stop, it keeps acquiring some left meters per second, and eventually it gets down to -2. All right, now here's the formula for that. Rise over run. Delta V is the rise, delta T, the elapsed time, the duration of the motion for this graph. It is the denominator, and that's the acceleration. That's basically the definition of acceleration. In this case, it's -4 meters per second. That's my vertical dimension of the graph, okay, with a direction -4 to indicate that it's sloping down from left to right. And then the duration is delta t, so that's 2 seconds. And then you take the quotient, and you get -2 meters per second per second. And students, that is the same as -2 meters per second squared. They both mean the same thing. Okay. I like meters per second because it kind of reminds you of what an acceleration is. For every second of travel, it tells you how many meters per second of speed you acquire or lose. Okay, so, all right, now, we know that the shape of the graph and the time axis form a polygon, in this case, a triangle. So, question, I don't know what this is, number 5. What is the area of the first distance triangle? And let me shade in the first distance triangle here. Okay, there it is shaded in. Okay. Go ahead and figure that out. Remember, what's the formula for the area of a triangle?
B squared plus B squared is C squared.
No, that's the Pythagorean theorem. Area of the triangle, 1/2 base times height. 1/2 base times height. And so if you have a graph like this, you can just look at 1/2 base times height. Bing. And this one, you can do it in your head. It's because it's nice round numbers and stuff. Okay. So no matter what you're doing, 1/2 times base is, okay, 1/2 base times height. Okay, 10 seconds to vote. Now, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for here. Yeah, pretty good. 1 meter is correct. And let's just double check it. Here's the calculation. Now, this is also the same as 1/2 AT squared, as we mentioned last time. But in terms of this diagram, it's pretty easy to eyeball it. So 1/2 base times height. So 1/2, i.e. 0.5. And then the base is 1.0 second. Yeah, that's the first half of this. Oh, where's my cursor? Here. That's the first half of the motion. So this width here is 1 second, and then the height is 2 meters per second. And so if you calculate that out, it's just a good old 1 meter per second. All right. And make a note, it's traveled on its way right. So you would go from like 0 meters to position 1 meter, for instance. You know, depending on where you start, you're after 1 second, you're 1 meter to the right of that. You know, whatever else you want to say. Okay, so C is the correct answer on that one. And just to remind you, that's also, in terms of a formula, see, this is a picture, and if you can think about 1/2 base times height, you're good, even if you can't remember 1/2 AT squared, or, you know, even if you're really nervous about using 1/2 AT squared. All you got to know is, you know, base area of a triangle, 1/2 base times height, and you're golden. All right? Now, this is gonna be in the YouTube, so let me cruise a little bit forward here. I want to continue. I want you to make a spatial map now. Now, this one is a physical map, where you could actually take photos of this bug or whatever it is moving from point A to point B and get a photo of it. Right? So this is, now we're not writing in the y-axis here, but you could if you wanted to. So there's the x-axis, and we just showed that it moved out to 1.0 meter to the right after 1.0 second of travel. And it started at 0.0, we'll just say that it starts at time t equals 0 at x equals 0. All right, just for convenience. Okay. And so now this is not an abstract graph. This is a x and y. You know, we don't really need the y-axis, but x-axis, yeah, this is good. Okay. And so this is a pair of snapshots of the yellow object as it accelerates and it's moving to the left. But now notice in this one you can't really tell anything about its speed. You have two snapshots, one at 0 seconds at the instant of start and then one at 1.0 second. But you don't really know what's going on in between those two snapshots. Unless, of course, you have the velocity graph. So that's right up here. Oh, to the upper right. Oh, I got to start going to yoga class or something. All right, so the velocity graph's over there. That tells you what the velocity's doing. This just tells you where it started, where it ends up at 1 second. Now, it happens to be that right there, the velocity is 0. So this is a turning point in the motion. Go ahead and make a note of that. Use the phrase turning point in the motion. And that is actually a significant, even all the way down into quantum field theory. The turning point in the motion of an object is something that physicists are always very interested in knowing about. If you've ever heard that word quantum tunneling, raise your hand if you've heard that word quantum tunneling. Couple people? Nobody? Not on TV? I thought The Flash does that. Don't they do that I thought they, or no, what was that show? Quantum Leap. That's where they do quantum tunneling back and forth through time. Anyways, I'll teach you about that this semester. Now, I want to do another iClicker question based on this spatial map, the x-axis mapping. Okay, now it's kind of a cinchy map. Okay, but we're going to add to it. We're going to add some more meaning to it in our study of it. And this is more of a brain burner. All right, so you ready? It's multiple choice. What is the position at time t equals 0 seconds? Da-na-na-na-na. And here's the velocity, or here's the distance triangle. I'll shade it in for you. Right there. Da-na-na-na-na-na. What is the position at 1.0 seconds? It's at x equals 1.0 meters. Nice. We already showed that. With the distance triangle, the first distance triangle. Now you got another one. Now what happens? Da-na-na-na-na-na. Oh my goodness. It appears that I'm catching some of you napping. But that's all right. We're learning. Think. 5 seconds to vote. 5, 4, 3, 2, 1, 0. Okay. And there is a spread of answers. Look at that. Okay, there's some people voted for 2. A bunch of people voted for 0. And a few people voted for the other 3 answers, including -1. But let's try to figure it out. Okay? It's 0 because this distance triangle, it's below the time axis. So the object is moving to the left through that 1 second time interval. Now, it's the same shape and size as the other distance triangle. It's just upside down. It's below the time axis. It's going to the left, so that means it's going to the left 1 meter. Okay, so it goes from 1 meter back to 0. All right? And so that's the interpretation of that. And make a note of that. The area under the time axis counts as negative if it's below the time, if your graph is below the time axis. Okay, because below the time axis means you're going to the left. So this person didn't go anywhere, and it's like, now what is your name again? Andrew? Yeah.
Me?
Yeah.
JC.
Okay, close. JC.
Yeah.
JC was saying, is it like a ramp? You go up the ramp, start at maximum speed, lose speed, stop, and then come back down the ramp. And yes, and then you end up at the bottom of the ramp again.
Yeah.
The same amount of time it takes to get up the ramp is the same amount of time it takes to get back to the bottom. That's kind of what we got here. Now,
Time it takes, like, stop, right?
yeah. Now, we're at this point, we stop the graph. We end the graph. We don't know what happens after this. It might keep accelerating, or it might go coasting at -2 meters per second, ad infinitum, off to the left. But for this time interval that we do know about, yeah, it goes back to 0.0 meters on the x-axis. All right, so it's kind of like this. Here's a kind of a, I've kind of looped it a little bit, but it's actually motion on the y-axis. So it goes over to the right, and then it bloops back around to the left, and it finishes at 0. So that's this kind of a graph. Now, if you have a different graph with a different slope and not the same distance triangles, like maybe a bigger one in the negatives, that's all right. You just let the numbers do the talking. That's what Galileo would say. The universe is this grand book, and it has this mathematical language. And so if you guys now know a nice piece of some of the chapters in that book, and you can let the numbers do the talking if you're awake. Now, if you're snoozing in the 4th row, which you don't want to do too often, but if you can do all this stuff when you're awake, or you can take a snooze. Now, don't be snoozing on me. Now, I want to. I saw a guy over here. His eyes were closed for a little bit. It's all right. Don't worry about it. So I want to go back and talk about something that we were talking about on Thursday. This was just a little bit of a workout. What I want to do is look at a velocity graph. Remember that we looked at it? It had a little bit of a curve to it. It wasn't just so we didn't have a straight distance rectangle or a distance triangle. And I said we had to use trapezoids. I'm going to show you how to do that now. So let's go to the document cam. And we're going to do a little bit of sketching. And can you switch me over to, can you turn on the document cam? And then switch to, and I'll use that pencil that's over there, I guess. No, wait a minute, I want to use mine. I think I'll use my stuff. Where's my, here we go. My pencil case. Okay, great. Now let me use this and this. No. Let me use this and this. And my graph paper. Okay. Let me go over there. Can you bring this chair over there? No, never mind. I'll use this big chair.
Okay.
let's get this over the. No, we- Now, I want to show you a graph like that, a velocity graph like that. And, we'll do a graph paper, and hopefully, I have to do this kind of sideways here. All right. All right. So this will be, whoa, it's out of focus. Oh my goodness, this is bad. How do we do this?
It's in focus now.
Is it?
Yeah, it auto-focused.
Focus? All right, let's try to draw some stuff here. Okay, so physical science, 721, 121. All right, now I'm going to draw a pretty big velocity axis. Let me draw my velocity graph, and then you can draw something like it. Okay, so here's my time axis, and we're going to assume that the velocity, so this is v and this is t over here. Now we're going to assume that it's not a straight line. It's not a straight line. It's going to curve. So let me do that pencil. All right, so I'm going to draw. Boy, this is hard with this table here. I'm going to start right here. Okay, 2 blocks up. Now you do whatever, if you don't have graph paper, maybe you can go 2 notebook paper ones up. Okay, now I'm going to go from there. Do you have a straight edge? Protractor? Anybody got a protractor or a straight edge? No nerds in here, no science nerds in here. Okay, we gotta use an emergency straight edge. We'll use we'll use my Costco card. Okay. So I'll use a Costco card for my emergency. Now, this is not the velocity graph. I'm just going to try to draw lightly. Now, you don't have to do this, but I'm going to do it so you can see. Okay, now I'm going to start at that degree of steepness for the graph. But by the time I get here, I'm going to be steeper than this dashed line. Okay, so let me do that. Here we go. So I'm going to start approximately the same, and then I'm going to get steeper and steeper. All right. So draw yourself a graph like that. All right. And this is the initial steepness right here. You can draw that if you want. Okay. I'm going to erase mine. Actually, don't draw that in. Just remember that's what it was. And I'm going to erase it because it's going to get in the way of what we definitely want to do. Now, the whole thing here is, let's draw a dotted line. I'll put a dot right here at the end, and then a dotted line down the time axis. And I'll make a note here. What is the area of this figure. It's not a triangle, it's not a rectangle, because it has the top of it's kind of curved. All right, now as I mentioned last time, the way that we tackle this is by taking little slips of it and treating them as an approximate trapezoid. So here's, I'm going to draw right here a little partition, a little slice of it, right here. Okay, one block across. And I'll just call this delta t. So that might be 1 second or 1 millisecond if it's something really changing fast. Okay? And that kind of looks like a trapezoid. Now, it's not a trapezoid because the top surface is curved. Okay, so I'm going to redraw it down below here with a little bit of exaggeration. I'm going to make it a little bit wider. And okay. Further. Okay, so here are the sides of it. So instead of 1 block across, it's 4 blocks. Now the true surface, I'm going to exaggerate the curve of it. Okay? And so, now that's a little bit exaggerated, but okay, and then here's the time axis. And so this is T1 and this is T2. And delta T is equal to T2 minus T1. Just the increment of time that we got there. Now, this one could be, if we're on a really precise system, this might be something like a millisecond. If it's a satellite out in space, actually, the GPS systems, I think they're even more precise than milliseconds. So let's just say that's a millisecond. Okay. Now, the trapezoid that we're going to work with is this one. And so I'm going to go to the top of my, so this is my actual figure, this is my true figure here. Okay. With a curved top. Now, I can approximate that and do the geometry for this trapezoid. Actually, I'll draw the top of it in red so you can see it. Okay, so that red line segment is how we approximate it. All right? So that's this little, and I'll just darken in this little slivery crescent here. Okay. So I'm trying to, now, my estimate is a trapezoid, which is easy. Trapezoids are, as I said before, they're a right triangle and a rectangle stacked on top of each other. So that's not too hard. And you can kind of see it here. You can mentally picture it. And I've got some slides here that are following that will, show the right triangles pretty clearly. All right? But my estimate is larger than the true area. Why is that? Because my estimate includes this little sliver here, this little slivery crescent that's not really in the true area. Okay? I've made my job easy, but at the price of overestimating. All right? Now, another thing that you can do, your second move, and I'll write this over here. I'm sorry, I have to sit sideways with this The second estimate is an underestimate. Still a trapezoid. Okay, so that would be a trapezoid, and I'll do this one. Do you have, yeah, you have another color like green or something? Nice. Well, TA to the rescue. Let's see how this is. Okay, now I'm going to draw I'm going to use my Costco card here. And I'm going to do an underestimate. And what I'm going to do is I'm going to draw a parallel line like this. It just grazes the sliver. Okay? So there's my so I'll draw it as a green trapezoid here. Okay, so there's my underestimate. Okay? So what you do is you do you do it again for each of these other ones. So here's another partition over here, another trapezoid, another 2 trapezoids. Go over here, another 2 trapezoids. And the last one, another 2 trapezoids. And then you got to do all these other ones here. So let's see, how many blocks have I got? 1, 2, 3, 4, 5, 6. So what we did? 7, 8, 9. I've got 9 blocks across in my diagram. So that would be 18 trapezoids. And then what you do is you add them up. You add up your overestimate, which is easy, and your underestimate, which is easy, and then you divide by 2. And that's an estimate of the true area, right? And that's how we do it. So you take the big estimate in red. Actually, let me draw the big estimate in red here. Okay, so that's like this. Okay, so there's the big one in red, the little one in green, and the true one has the curved surface. So and that'll give us a little bit of plus or minus for my estimate. You know, it's not going to be perfect, but it's fairly close. And if it's close enough to land a rocket on the moon, you're golden. All right? But if it's not, then you make smaller delta T's. Do it again. So divide each of these 9 subdivisions into 2, and that gives you 18 subdivisions now, and so 36 trapezoids, and then check your figures. Okay, and if that's accurate enough to land on the moon, you're golden. If not, do it again. You know, go from 18 to 36, 72, 140, you know, as many times as you need to get the precision that you want. Now, in Hidden Figures, this is the kind of things that they were doing. And we're doing it on pencil and paper, and so were they. All right? Now, today we have computers to do it. But back in the day, no, they did not. Okay, now we're going to go back to the laptop. So let me get my grading implements here. Get a Costco card first. I don't want to do this here. People go to Costco. So get my... Actually, that would be good. They spend the money, I get the benefits. I get the bonus dollars at the end of the year. Switch me over to the laptop, please. Over here. Okay. All right, we're back. Now, what I'm going to do in this slide, I'm going to embed a photocopy or a scan of what we just did. Now, you'll have it in your notes if you took notes. And if you don't, it'll be in YouTube. So let's keep going. All right, so so now I'll write it out as an outline. Okay, so let's just review. You know, the slivery crescent at the top of the figure, that shows how the first trapezoid overestimates the true distance, which I'm going to show you in yellow here. And then number two, you then compensate for that by constructing the green trapezoid. Actually, everything in this picture is green. So, but in the diagram on the dot cam, it was green, and that's the underestimate. And then you just take the average, the overestimate plus the underestimate, and divide by 2. Now, it's not perfect, but sometimes you have to. Sometimes all the calculus in the world won't get you a formula, so you just got to do it this way. And the thing is, they can usually, using radar, they can always track the velocity of something. Just like a cop's nabbing you nabbing people. I know nobody in here disobeys the speed law, but there are individuals that have been nabbed by cops and using the speed gun, and that's how NASA does it a lot of times. Sometimes they just do it by triangulation, calculate hypotenuse and time and all that stuff, but off of a film. But so let's take a look at this. Now here's the overestimate. All right, and here's the crescent. All right, that little slivery crescent. Now I'm going to bash that over here to the right. And let me put my overestimate trapezoid. So there's the trapezoid. It's a rectangle with a right triangle sitting on top of it. Okay, so if you know the two speeds, okay, you can figure out your right triangle. And then if you know the delta t, you can figure out the base of the triangle and the rectangle too. So you're golden at that point. So the height of the rectangle is the first speed that you measure. So that would be like this speed right here. So you measure this with your radar gun. Okay, you measure it up here with your radar gun. Now the true shape of the curve is this curve, but you're overestimating it with this right triangle. So you have delta y from the radar gun, and then you have delta t, probably also, if you pulse your radar gun at a certain pulse rate, like 1 every millisecond, then you know what delta t is. And you just, build up a bunch of trapezoids like this. So the base of the rectangle is, the height of it is velocity 1. The width of it is delta t. The right triangle, the width of it is delta t, and the height of it is velocity 2 minus whatever velocity 1 was. Okay, so delta v up there. All right, and then you just do 1/2 base times height up there, and then down here for the rectangle, base times height. Ding, you got it. Okay, you could do it on a spreadsheet if you wanted to. And that's what these hidden figures people, the calculators were doing. Just doing it over and over, ultra precise as they can. All right, now the underestimate. So here's the true in yellow. Okay, so that's the true. That's the one we're trying to figure out as close as we can, as precisely as we can, because we don't want the astronaut to land in the plains of Spain. Okay, we want him to land near the Bahamas or somewhere near Kennedy Space Center. Okay, or somewhere near the Philippine Islands, where the Navy can catch them over there. The Apollo astronauts landed in the Pacific Ocean, apparently, but most of the other astronauts landed in the Atlantic, in the Bahama area, if they were on target. Okay, so there's the true, and then the underestimate is here. Okay, so that's the underestimate that we sketched in. Again, a different. It's a right triangle and a rectangle sitting on top. Okay, right triangle sitting on top of a rectangle, but it's a little bit smaller. Okay, now I'm gonna take out the graph paper sketch, and there they are. And that's just a rough set of estimates. If you were doing this on a computer, you would I didn't estimate the height from here to here. I just kind of eyeballed it so I could teach you about it. But if you were up there in Langley, NASA Langley, or NACA, Langley, NACA, between from World War II, after World War I, all the way up to the late 50s. It was NACA, and then it became NASA in the late 1950s. All those trapezoid calculations were done by humans like Dorothy Vaughan in Hidden Figures. And then, which is good, it just takes a lot of time. And they did a lot of aeronautical calculations for, like, World War II fighter aircraft, how to design them so that the range was as big as they could get it, and the payload was a certain, and bombers, how to, make sure that the flight was stable. They used wind tunnels and all, did all kinds of testing on, and they still do it up there on spacecraft and aircraft and stuff like that. But after about the 1960s, the late 50s, when IBM started delivering the big machines to NASA and Los Alamos and stuff like that, then all the trapezoids were calculated by the machines. However, who was in charge of the machines? Dorothy Vaughan. So, let that be a lesson to you. A lot of people get nervous about computers, and computers can cause a lot of mayhem. But they're never going to take over the world because they're always programmed by humans. Unless you're, Dr. Evil. But Dr. Evil is only in movies. And what one computer programmer can program, somebody else can program against it. So we have Dorothy Vaughan and other people like her that were running those computers. And let me just let that be my last comment about that movie, Hidden Figures. It's a great movie. And there's a lot of, mushy stuff, romance and all that stuff. I don't know how much of that was real. But, the drama of working in that center under conditions of segregation and then integration, that was real and good. And the calculations, of course, were real. So let's get back to free fall. I've shown you how they do powered flight with a changing acceleration. Let's go take another look at something, not a velocity graph, but another look at free fall. And here's a lovely photo. If you watch golf on television, sometimes you see them. I don't know what kind of equipment they have to do this, but apparently they do it at football games now too, where they actually track the arc of the golf ball. And they've got this one. It looks pretty good. It looks like a pretty nice parabola and stuff. But the main thing to remember here is that acceleration due to gravity is a negative number of meters per second per second. All right? It's negative 9.8 meters per second, or negative 9.8 meters per second squared. Both of those mean the same thing. So that means you lose upward speed if you're moving upward. You gain downward speed if you're moving downward, just like this arc. It loses upward speed, and then right about here at the top of the arc, right? See, I'm doing this left-handed and over backwards and upside down. Right? Oh. Come on, Doctor. Well, I'll put my cursor right about here where my cursor is. I can't get the tip of it to the right spot. Right there, that's the top of the arc. Now, right there, you've lost all your upward speed. Okay? You had some. She had some when she hit the ball. Okay? She had some horizontal speed as well. Okay? Because it's moving across the green, or the fairway, I guess that is, heading for the green. But she had some upward, and she lost all of it by that point up there where my cursor is. And then after that, it started gaining all of it back. All right, so let's take a look at another velocity graph, and let's try to, what we're going to do is put together Galileo's equation all the way. Okay, we've got distance triangle with the drop distance formula, and we've got the speed times time formula for constant acceleration. Let's put it all together. So here's your velocity graph, and we know how to handle this kind of an area. Okay, the distance traveled is equal to the area under the graph. So that's the red line. So that's this trapezoid. Now this is for constant acceleration. The rise over the run is a constant, and this is speeding up to the right. So it's going to the right, and it's moving faster and faster. Okay. All right, and we can handle that. And here's how you do it. And, you know, if it's a trapezoid shape, right? So let's just break it up into a trapezoid and a right triangle. So we have a right triangle, we have a rectangle. Let's split them apart. Okay, so there's the right triangle, there's the rectangle. So let's split them out there. So we're kind of breaking it apart, and we're going to put it back together into one expression. Now we know how to handle a distance triangle. That's 1/2 AT squared. That's what we call a walk in the park. And we definitely know how to handle a distance rectangle. That's speed times time. That's not just a walk in the park. That's a walk in the park with an ice cream cone. All right, so you're really cooking with those two. Okay, so you compute each of the sub areas separately, and that's what Galileo's equation does. You know, here's the pair of equations. You know, for the distance triangle up there, 1/2 AT squared. That's a walk in the park, my friend. And then the rectangle, speed times time, v times t. And what we'll do is call it v subscript I times t. Okay, initial speed. You know, so vi is this. Oh, where's my cursor? Boy, let me turn around this way. Maybe this will give me a different outlook on life. Okay, here, this is better. Okay, so vi is over here. Okay, that's your initial speed. And then vf is up here, you know, just like we were talking about with hidden figures. But this is exact. Okay, so you're speeding up. Okay, and vi goes here, so initial speed. And that's for this distance rectangle. Now, vf and vi are inside. They're encoded in a, the acceleration, because the acceleration is delta v over delta t. Okay, so delta v is, in this case, vf minus vi. Okay, so inside the numerator of a, whatever a happens to be, is vf and vi. Now, you put them together. Your total change in the x coordinate to the right is the sum of the distance rectangle plus the sum of the distance triangle. All right? And what we're going to do now, oops, let me go back. What we're going to do now is we're going to apply that base. So this is the generic idea here. All right? This is for any horizontal acceleration. Now what we're going to do is apply it to free fall. And free fall is just, it's going to look the same, except it's going to be delta y, and it's going to be a vertical component of the speed. And remember, this is a velocity graph, so it's not a picture of the actual trajectory, where the ball is going or where the object is going. But we're going to do that here. So let's look at what Galileo would say. This is from one of his books. If now we examine the matter carefully, we find no addition or increment more simple than that which repeats itself always in the same manner. In other words, every second of measurement, you get another negative 9.8 meters per second. All right. So if he was writing a table, and if Galileo was to say, okay, I'll drop it from rest and then start my stopwatch, then he would get a table like this. Okay, starting it from rest at time t equals 0, no speed, it's at rest. Then after 1 second, 9.8 meters per second downward. After 2 seconds, 19.6. After 3 seconds, 29.4. After 4 seconds, 39.2. etc. So go ahead and write that table and make a note that the direction is downward because it's, it's off the Leaning Tower of Pisa, etc. And so this is like saying the increase repeats itself always in the same manner, always another 9.8 meters per second of downward speed. All right? Now, I'm going to go to the next slide and just reinforce this is the value of g. Now, usually in textbooks and stuff, they'll just write it down as positive 9.8 meters per second squared. What I've been doing lately, the last few years, is always writing it down as a negative. But this is all right. You'll see it this way. You just got to remember that if you're actually trying to use y coordinates up and down, instead of just figuring out a distance, then you have to use negative 9.8. So acceleration is delta v over delta t in general. Now, here's the drop distance formula. And I think this is actually the very first velocity graph we did. We started at rest over here. And then we acquired negative 9.8 meters per second after the first second of travel. After 5 seconds, we had, or actually, this is 4 seconds down here. We had negative 39.2. All right. Now that's a velocity graph. This polygon is the distance triangle for it. All right. 1/2 base times height, but it's negative, okay, because it's below the time axis. So 1/2 base times height, and then that leads to 1/2 gt squared. Okay. So for a drop, now, and this is using just positive g. So if all you want is the distance that you drop, you don't really care about what y coordinate you start with and stuff like that. Then just use positive 9.8. So what we found is that this formula here, delta x times VIT plus 1/2 AT squared. If you assume that it starts from rest, it basically boils down to 1/2 GT squared. All right? And so to figure out then this would be delta y, okay? Or the vertical distance that you drop. Now, it's about time to dismiss. So I'm not going to give you any homework tonight. I know that hurts your feelings. But next time we're going to do a free fall example from the Mines of Moria to start class. And then we'll talk a little bit more about equations of free fall. Okay, no homework tonight. Just start reading chapter 2, however. That'll be helpful. You're dismissed. Question?
So I wasn't here last week, and
Yeah.
I sent you an email for the first homework. I didn't do it because I was in the hospital. So I have the paper to show you.
Good. Okay. Can I have a copy? Do you want to give it to me, or can I have a copy of it, or
I can make a copy.
make a copy and give it to me on Thursday?
Okay.
Good.
Hey, so did you still not get
Yeah.
any of my registered clickers?
I'll check it right now. Let me shut down everything. Gotta get my clicker back over here.